Now let us talk about a corollary of Maa-ler's compactness criterion that frequently appears in dynamical systems. This criterion is about the divergence of a trajectory in a homogeneous space. Let G sub t's parameterized by the non-negative real numbers be a subset of SLDR. In practice, this is usually a one-parameter subsemigroup of SLDR, but here we don't need. We just make this to be any subset. Then, the sequence the trajectory G sub t times SLDZ, which is parameterized by the non-negative real numbers. And remember that this is a subset in the homogeneous space SLDR mod SLDZ. Diverges. What I mean by saying diverges is that this trajectory, this subset parameterized by non-negative real numbers, has no limit points. In this homogeneous space. And this corollary of Maa-ler's compactness criterion says this happens if and only if for each neighborhood omega of 0 there exists a T0 such that for any t greater or equal to T0, the lattice G sub t times z raised to the power d contains a non-zero element belonging to omega. Here, two objects gt SLDZ and gt z raised to the power d are really the same object through the identification. Recall that we have the identification of SLDR mod SLDZ, the space of unimodular lattices in RD. So this left coset is naturally identified with G times ZD, the standard unimodular lattice in RD. Previously, when stating the Mahler's compactness criterion, we used the right coset space, which is identified with the unimodular lattices in RD in this way. The right coset SLDZG is identified with G inverse times ZD. And here we are going to change our language a little bit. If you change this to left coset space, namely if you move G to the front, then this G inverse will become G. I hope it's not hard for you to switch between those two languages. And remember that we also made a remark that if you use one language, you must stick to it. Namely, if you use the right coset, you cannot identify this with this left multiplication by G. You have to use G inverse, otherwise something weird will happen. Okay, anyway, we're going to state this corollary by using the left coset space, which seems to be more common in the literature of dynamical systems. And here's a proof of this corollary, which is not hard. For the forward direction, let's prove the contrapositive. Suppose, on the contrary, that there exists a neighborhood omega of 0. So I use this circle to denote the neighborhood. The circle looks like the initial of the word open. Hope this is easy for you to understand. Such that for any t0, there exists a t greater or equal to t0 with g sub t zd intersection omega is trivial. Namely, it only contains the origin. And it follows that there exists a sequence t sub k going to infinity such that g sub tk times zd intersection omega is trivial for any k. So what does this tell you? I'll let you think about it first. This tells you that the sequence of lattices is precompact. So by Mahler's compactness criterion, the sequence gtk times zd is precompact. So what do you know from the precompactness of a sequence? Because you know that the sequence can be identified with this sequence. The left cosets gtk times SL dz in this homogeneous space. But this quotient is Hausdorff, and thus the precompactness is same as the pre-sequential compactness. So this tells you that there exists a convergent subsequence of this sequence in this homogeneous space SLDR mod SLDZ. Okay, now what do you see from this? On the left hand side of the statement of this corollary, you should be able to see a contradiction, because we got the convergent subsequence in this homogeneous space, but the left hand side of the statement of this corollary says that this trajectory should not have any limit points in these homogeneous spaces. So this is a contradiction. Contradiction to that this trajectory has no limit point in this quotient. So we completed the half of the proof. Now conversely, suppose that you have a non-divergent trajectory, which means it has a limit point in this quotient. Say this sequence G sub tk times S of dz where k is from 1 to infinity converges. It follows that because a convergent sequence in this quotient space is always precompact. This is a fact in general topology. A convergent sequence is always precompact. You just take a neighborhood of the limit of this sequence that contains all but finite many elements in this sequence. So if you take any neighborhood of the limit of this convergent sequence, since this space is Hausdorff, the limit must be unique, and that neighborhood must contain all but finite many elements in the sequence. So the sequence union its limit must be a compact subset of this space, which means the sequence must be precompact. However, by the Maa-ler's compactness criterion, a precompact subset in the space of unimodular lattices must stay away from a small neighborhood of the origin. So we have a neighborhood of the origin. So this notation in my lecture series always mean a neighborhood such that G sub tk times zd intersection omega is equal to just the origin, no other point, for any k greater or equal to 1. But this contradicts to the right-hand side of the corollary we want to prove. Here I should emphasize that by saying has no limit points, I really mean it has no limit points as t goes to infinity, so that you can choose the subsequence so that those subscripts go to infinity as k go to infinity. So g sub tk zd intersection omega is trivial for any k greater or equal to 1, and this tk will go to infinity. And that contradicts to the right-hand side of the statement of this corollary, which says for each neighborhood of 0, there exists a t0 such that any t greater or equal to t0, this lattice g sub t zd contains a non-zero element in omega. So I should emphasize this earlier in this definition of divergence. And this finishes our proof of this corollary. And the Maa-ler's compactness criterion, together with this corollary, will be the foundation of the so-called Dani's correspondence principle, which I am going to introduce later.